Okay, good afternoon, everyone. I'm Chen Lin. So today I will present our work on overall control for scaling WeChat microservices. So this work is a joint work with National University Singapore and Columbia University. So WeChat is a mobile app and very popular in China. So it not only can serve the chatting, but also it provides a social networking like the moments, and also we provide the payments called the WeChat Pay. WeChat is the most popular mobile app in China. So in March this year, WeChat already reached 1 billion monthly active users. So most of the users are China-based. We know that in US and the Western country, we all use the Telegram, WhatsApp, but WeChat actually is handling 1 billion users, and without this amount of users, the WeChat backend have to deal with thousands of billion messages per day. So it's inevitable to deal with the overload scenario in the backend. The WeChat backend is constructed based on the microservice architecture. So microservice architecture is a special version of the service-oriented architecture. So the service-oriented architecture decomposes the traditional service into many sub-services. So the sub-service is connected by network. So these services can form a service DAG. So the vertex in the DAG represent a distinct service, and the edge represent all parts. So in WeChat, we have many kinds of microservices. We categorize them into mainly two types. One is the basic service, means the out degree of the vertex in the service stack is 0. And the other is the lib service. Lib service means that the other service that the out degree is not 0. That means the lib service will call other service in the service stack. Especially, we distinguish one kind of lib service called the entering lib service. That is that means the in degree of the service is 0. For entering lib service is the first service that reach when the user request reach the service backend. So for the service design, for service design, it's very hard for the developer to estimate the dynamics of workload during the development of microservices. Because most of the time they focus on the business logic and they cannot estimate the workload dynamics accurately. For overall scenarios, actually we formalize it as 3 types. One is the most simple way, so that means the upstream service call the downstream service, and the downstream service get overload. The second is that the second type is that the upstream service may call the downstream service multiple times. So the success of the upstream service is determined by the consecutive success of the calling to the downstream services. The third type is the most common types, means the upstream service may call different downstream service, and all the downstream service get overload. So for the first type, we just name it as a simple overload scenario, and the second type of the second and the third type of the scenario called it subsequent overload, because we have multiple call to the downstream services. For over control, one naive solution or approach is by random load shedding. Is random shedding helpful? For simple overall scenario, random load shedding is useful because they guarantee the uniform distribution for load shedding. But for subsequent overload, the answer is not. You may consider that the downstream service has some, when downstream get overload, it has some possibility to reject the request. So in this case, if the upstream service need to call the downstream multiple times, and the probability of the downstream time of each call will make the upstream service of very low success rate with the random load shedding. But at the meantime, the downstream service still have to deal with the request that will be destined to abort for the upstream service request. That means the downstream service still have to be busy with the partial processing of the upstream service request. This makes the system get busy and cannot benefit from any of the random load shedding. Another problem of handling the overload is that the workload in WeChat is changed in a very high degree. So in a daily statistics, the peak request rate is 3 times higher than the normal and the average request rate. And in some special period, for example, the Chinese Lunar New Year, the request rate is around 10 times higher than the normal days. So although we can over-provisioning the server to handle the load surge in this scenario, but the solution is not economic and very difficult to manage. So we still want to devise some mechanism to handle the load surge while maintaining the best effort user experience. That's our motivation to develop the overall control mechanism. So the overall mechanism in WeChat backend is called DAGOR. So DAGOR is actually dealing with the 2 things. One is the overall detection. The second is the service definition control. Not that complex. Only do with 2 things. But we have raised several requirements to do that. First is the overall control must be service agnostic. That means the overall control should be applicable to all kinds of the microservice. Recall that we have more than 5,000 microservices at the WeChat backend. So the business logic of the microservice are quite different, but we apply the same overall control for this microservice. So this can benefit the ever-evolving microservice system because the WeChat is evolving very quickly. A lot of new services online and the new configuration need to update every day. This also benefit the system to decouple overall control from the business logic, so that our overall control framework can scale to more microservices. The second requirement is independent but collaborative. Independent means that the overall control must be totally decentralized. That means the overall controls rely on the capability of single node to control their overall situation, rather than counting on the centralized gateway to monitor the overall situation in the whole system. And we also want the overall control to be service-oriented cooperation among the nodes. That means the upstream services and the downstream should work together to prevent the partial processing of the requests that are destined to abort. The third requirement is efficient and fair. because we want to maintain the user experience to even the overall purpose. So we need to sustain the best effort success rate when load shedding becomes inevitable. And also, as we have analyzed in the previous slides, we have 3 types of overall scenarios. We don't want to provide to emphasize any bias on the overall scenario. Even the microservice calling path is very complex. We still want different kind of requests share the same rate of overall load shedding. So the first one is overload detection. Overload detection, we choose the indicator. We need to choose one indicator to monitor the load in the node. So our choice is the queuing time. The queuing time is the average waiting time of requests in the pending queue. So for each request, its queuing time is measured by the time difference between the request arrive at the server and its processing starts. So this is the reason behind choosing the queuing time is that the queuing time can accurately reflect the load status of a single node, whether it is overload or not. And also, this is related to our service level agreement, because in most of the service development, our engineer are more care about the service agreement. For example, if the service agreement requires the request to get response in 100 milliseconds, but if the queuing time is so long, even the request get processed in after the queue is doing a wasting job. So one immediate question is that why don't we choose the response time that is quite common in other overall control system? So the response time is not accurate, and we have tried that, and we also provide some experiment to evaluate that. The response time will involve some false positive of the overall, so we don't choose that. And also other indicator, the CPU utilization. CPU utilization is very intuitive, but it's not a right indicator, because even a server is of high CPU utilization, it may still can process the request very quickly, so it's not overload. So another design for the DAGOR is the service admission control. So in WeChat, we internally prioritize the services based on the business significance and user experience. So, for example, for the login is of the highest priority, because if you can't log into the app, you can't do anything. And also, the payment have higher priority than the instant messaging. So this is the first level of the prioritization, and this is static for all the requests. But we have observed that partially discarding the request with the same business priority will cause the issue of subsequent overload, because the requests are actually discarded and rendered within the same business priority. So we further define a user priority to make the overall control more fine-grained. The user priority is not static; is generally based on a hash function taking effect on the user ID. So this will reshuffle on an hour basis. the reason is that we need to maintain a relatively stable service for a user, and on the other hand, we want different user to have grant the chance to have the high priority in a daily basis. So we also exploit a histogram for a fast adjustment of the automation service level. So here is the workflow or overall workflow of the DAGOR. When a request reaches the service backend, we will assign a business priority and a user priority for each services, and the priorities will be encapsulated into the header of the services, and it will carry in the calling path of the microservices. So when a service node receive a request, you will perform the automation control. If the automation allow the service to send to the downstream services, then you will send a new request with the same business and user priority. So when the service gets send the response to the upstream service, it also reply its business and user priority to indicate its low status, so that it can perform the collaborative automation control. That means the upstream service will perform the local automation control first before sending out the request. So we finally review, evaluate our solution based on the approach we have present. First is the overload detection. We compare the queuing time and the response time. We have seen that the queuing time actually provide the highest success rate for the service. Because as I mentioned before, the response time will involve the false positive, even the service node is not overloaded. Then we compare our mechanism with the other overall control mechanism called CODA and SADA, and we also calculate the optimal success rate. The optimal success rate means that we calculate the feed rate when the system just saturated, divided by the actual feed rate, and we can see in the figure that DAGOR almost reached the optimal success rate. So this is the last result. We compare the fairness of DAGOR against the CODA. We can see that CODA only favor the simple scenario. Simple scenario means the M1. M1 means that only call the downstream service once, and M2 is twice, and so on and so forth. But for DAGOR, all the any feed rate and any low situation, all the service get almost the same chance to be shared. So to summarize, we want to share several design principles of DAGOR. The first is that for overall control, especially for the large scale mobile service backend, must be decentralized and autonomous in each node and services. We shouldn't count on any centralized component to do that. The second is you need to employ the feedback mechanism for adaptive load shedding. For example, when we choose the queuing time because we need to control the queue length. So for manual configuration, it's very hard to design what is the right length. But with the feedback mechanism that between the downstream and upstream, we can configure the threshold automatically. The third is that we need to take into account the user experience as the first class citizen. So that's all. Thank you.